Hi everyone, welcome to 9.6 where we explore radical functions. So to see what a radical function looks like and how it behaves, we're going to first graph some parent functions. So the parent functions you see listed below involve root symbols. So we've got the square root of x, and again, this square root symbol, just to make it super clear, we're looking for the square root of x. We're going to also graph the cubed root of x. We're going to graph the fourth root of x, and we're going to graph the fifth root of x and see how those graphs behave in comparison. When we make these sketches for these graphs, based on what we see on your calculator screen, we're going to explore the domain, the range, where the graphs are positive and where they're negative. So if we start with your graph, y equals the square root of x, so second function and hit your x squared key. So we've got the root of x. From here, when you hit graph, you notice that the graph sort of starts at the origin and increases as you trace it from left to right. A quick look at the table of values will show you something interesting here. So what you might notice is that for all the x values that are 0 or positive, you have real y values. But for x values that happen to be negative, all we're seeing are errors in this table of values. So if you can imagine why that's the case, going back to your equation, the square root of x can only be a real number if x is 0 or positive. So we are reminded that we can't take the square root of a negative number. So that's why negative x values for this particular graph don't show up. So they don't give us real values to actually graph. So make a sketch in your notebooks of this type of graph and make sure you clearly label it as the square root of x. The second function we want to explore might have a slightly different behavior. So I'm going to clear root x out of the mix here, and I'm going to type in the cubed root of x. But in order to retrieve a cubed root symbol, you need to go to your math key. So if you look at math, you've got a cubed root as option 4. So arrow down to option 4 and select cubed root. So if we wanted to find the cubed root of x, again, put x in as your radicand. Once you hit graph, it kind of looks like a square root function on the right side, but there's graph to the left side of this. So this graph does increase as you trace it from left to right, but this time there are negative x values that give us real y values on the graph. Again, if we look at your table, second function table here, we can see that when x is, let's say, -6, we get a real y value. The reason that is for this particular case, yes, it's a root, but we're talking about a cubed root. Please be reminded that you can take the cubed root of a negative number, but you can't take the square root of a negative number. So the next graph we wanted you to explore the behavior for was the fourth root of x. Now, if you look at your math key, you see option 5 here says x as your index, and it's telling you it's the x root. So you get to pick the type of root it is if you choose option 5. But if you choose that option, you have to make sure that you've cleared your graphing screen. And if we want the fourth root of x, you have to type the 4 in first. So 4, and then hit your math key, arrow down to option 5, and here now we're saying, okay, 4 is populating that index, so we've got the fourth root of x. So when you hit graph for the fourth root of x, this one, once again, kind of looks like a square root function, but it's more extreme. So it's increasing at a different rate than x squared. If you're not sure, you can graph them both and compare. So if we are, square root of x. If we graph them both, so second function, root x. So our red graph is going to be the original square root of x, where the fourth root of x is going to be the blue graph. When you compare these two, the square root of x will increase at a faster rate or more steeply, while the fourth root of x has a more gradual increase when you trace it from left to right. So these are both roots with even indices. If we go back to your y equals screen, we can clear these both out. And the last graph we wanted you to compare with was the fifth root of x. So once again, you have to put the type of root in first. So 5 for fifth root. retrieve that math radical symbol under your math keys. So now arrow down to option 5 for x root, or the type of root. So you see it's populated 5 as the index. So here's the fifth root of x, and again when you hit graph, it kind of looks like the cubed root of x. So there's behaving, those odd index types of graphs are behaving in a very similar fashion. Now, if we were to graph the cubed root of x at the same time, just to compare them, it's probably a good idea for us to do so. So if we hit math and option 4 for cubed root, and we graph the cube root of x, so be mindful that will be the red graph that appears on your screen. We can see that once again, that red graph is reaching higher. It's not as flat as the fifth root of x. So the behaviors are very similar. They're both above and below the x-axis in the same locations, but how quickly they're increasing or how sharply they're increasing is very different. So I would suggest that the higher the index, when you have an odd index, the closer those lines are going to hug the x-axis.
So to recall how these sketches behaved, we can say y equals the square root of x. We sometimes call it the eyebrow. It sort of looks like an eyebrow shape. What happens is it starts at the origin 0, 0, and it increases as we trace it from left to right. What we can say about the domain of this function, and I just want you to recall that domain means how far left to how far right does this graph go. The x value of my domain starts at 0, or right at the origin, and that graph continues as we trace further to the right. So we say the domain is from 0 to infinity. The range of this function, remember, think low to high or bottom to top. The lowest y value on this function is right at the origin, so it has a y value of 0. And the highest y value is positive infinity because that tail increases and sneaks its way towards the sky. Now, aside from that, we're looking for where this graph is positive and or negative. So by positive, we mean where is this graph sitting above the x-axis? And the whole graph is sitting above the x-axis, but we have to say that it's positive from 0 to infinity. So if we trace along our domain from 0 to infinity, the graph is going to sit above the x-axis. But we're not allowed to include 0, even though it's a point on the graph. If you were to put your pencil on 0, you're not completely above the x-axis. You're actually right on the x-axis. So we say the graph is only positive from 0 to infinity. The second function we graphed was y equals the cubed root of x. So if we sketch that function, it sort of looked similar to this, sort of an S shape. What we can recognize this time is it has a very different domain. Because we can take the cubed root of positive or negative numbers, the domain of this function is from negative infinity to positive infinity. So there are no x values that we exclude from the domain. The range of our function, low to high, now this leftmost tail sneaks down towards the floor while the rightmost tail slowly sneaks towards the sky. So we would say the range of this function is also negative to positive infinity. This graph is positive or sits above the x-axis from 0 to infinity. And if I highlighted that positive section, this is the section we're referring to. Remember, positive sections are sitting above the x-axis. This graph also has a negative section. So in terms of negatives, I'm going to highlight this in a different color here for you. The negative section of the graph is going to sit below the x-axis. So the green highlighted segment that I'm just showing you here is going to be the negative part of the graph. But again, it needs to be written in interval notation from left to right in terms of your x values. So this graph is negative from negative infinity, meaning as far left as you can imagine, until we hit 0 or the origin when it starts to cross and move above that x-axis. So we've now evaluated the domain, the range, where the graph is positive, and where the graph is negative. We can do the same thing for the third graph, which was y equals the fourth root of x. And the fourth root of x looked very much like the square root of x. It had the same type of behavior. We know that the domain of this function, once again, was from 0 to infinity. We know that the range of this function was also from 0 to infinity, and the graph was only positive, so it was only sitting above that x-axis, and it was positive from 0 to infinity. And once again, we can't include 0, even though it's a point on the graph. If I put my pencil on x equals 0, I'm sitting right on the x-axis. I'm not necessarily above it. The last function we wanted you to analyze for behavior was the fifth root of x. And the fifth root of x looked very much like the cubed root of x because it had an odd index as well. So it also had a tail that moved or could be traced from left to right indefinitely. So we say the domain of this function went from negative to positive infinity. The range of this function, low to high, is also negative to positive infinity. And then when we inspect parts of the graph, you do have a negative segment of the graph initially, and then that segment transitions to something that's positive. So then we have a positive part of the graph on the right side. So we would say this graph is positive from 0 to infinity, and this graph is sitting below the x-axis, or negative from negative infinity to 0. So your takeaway from this is that when you have a radical function, if it is an even index, it will behave like root x or the fourth root of x. The difference is that the rate of increase will change. If you have a graph that has an odd root, then you're looking at something like the cubed root of x or the fifth root of x. And again, those will behave in very similar fashions because it's okay for us to take the cubed root or the fifth root of a negative number. So we see the tails or domain of the graph stretches to the left of 0. But again, that's going to be one of the most notable differences between odd and even indices and roots. So in summary, if you're given the square root of x or the fourth root of x, the domain and range are always going to be the same. Domain is from 0 to infinity and range is from 0 to infinity. The positive and negative intervals are also the same. So without sort of getting into specifics, we know an even root function will look something like this. It will look something like our eyebrow shape. This graph will always pass through the origin, but in comparison, the fourth root of x is going to rise more slowly than root x. And by slowly, we mean it's sort of tighter to that x-axis. If you are graphing instead an odd root function, so the cubed root of x or the fifth root of x, then again, domain and range are the same, but the shape this time looks a little different. It's kind of like that funky S-shaped graph. So when you have an odd index, we know the domain and range are both going to be from negative to positive infinity. Again, this graph is going to pass through the origin in its original state, but the cubed root of x is going to rise or fall more rapidly. So what that means is if we have the fifth root of x, again, those tails are going to hug that x-axis a little bit tighter. Now that we understand how these radical functions behave, we're going to show you how to transform them. And by transformations, we're talking about things like horizontal shifts. So how do we move this left or right? We're talking about vertical shifts or moving the graphs up or down. We're going to look at vertical stretches or shrinks. So we're looking at making the graphs narrower or wider or changing that rate of increase. We're also going to be exploring how reflections can be done. Just as a reminder, when you have a horizontal shift, this is a change in your x value. So we would say if you start with the square root of x, and I'm just going to use square roots as my examples, this will work the same for cubed roots or fourth roots. All radical functions will have the same type of impact on these transformations or with these transformations. If we then take and add or subtract something to that x. So let's say we've got x plus 5 as an example. That kind of transformation is a horizontal change, and we know that horizontal changes are backwards logically. So plus actually means move to the left by 5 units. So if I were to sketch the square root of x, and I were to sketch the square root of x plus 5, I know I have to shift that original point from 0, 0, 5 units to the left. So it still opens the same way and holds the same shape, but it's further to the left than it was originally. So these kinds of transformations behave very much the same as the transformations we explored in earlier sections of this module. If you have a vertical shift instead, so we know that vertical shifts move up or down. An example of this might be y equals the square root of x becoming or being transformed as y equals the square root of x. Now we close that radical, and then maybe we have something like minus 3. So remember, when you add or subtract a constant from the end of your function, so after that root, after that radical, or after that bracket, that's going to cause a vertical change. So once again, if we graphed root x, we know that's the eyebrow shape, but the square root of x all minus 3 means we're going to move that shape 3 units down from its original position. So instead of starting at 0, 0, we're now starting at 0, negative 3. So again, we can draw that shape and it behaves the same way as the original function. It's just been relocated. Last, or next, I guess, we've got a vertical stretch or shrink. We'll just call these a stretch or shrink. They are vertical stretches or shrinks. But if you have something like y equals the square root of x, and all of a sudden we multiply that radical by some other number, so let's say that becomes y equals 4 times the square root of x, that's going to cause a much steeper increase. It's not going to relocate your graph, it's just going to make it rise 4 times faster. So if we compared those two graphs, you would noticeably see a more rapid increase with this function. So again, that would constitute a vertical stretch. If we had a vertical shrink, then that value of 4 would be something between 0 and 1. So we know that if you have a fraction value that's between 0 and 1, you're going to have a shrink instead. So it will rise at a much slower rate. The last types of changes we want to explore or remind you of are reflections. And you can have one of two reflections. You can have a reflection across the x-axis. And we know if we reflect something across the x-axis, then your negative sign needs to be inserted in a very specific spot. So if y equals the square root of x becomes y equals negative the square root of x, what happens here is we can see that it creates that mirror image across x. So you go from your original radical function to something, if you can imagine imprinting that graph across the x-axis or folding this grid along the x-axis and making that imprint, you would all of a sudden have a graph that was sitting underneath the x-axis and is decreasing instead. So this constitutes a reflection across the x-axis. If you want instead a reflection across the y-axis, we have to reposition that negative sign. So if we want that reflection across the y, we know that it doesn't mean a negative in front of your radical. It actually means we need a negative in front of the x. So this is going to be y equals the square root of negative x. What this would appear as, again, here's your regular root x. If you have y equals the square root of negative x, you can imagine folding your original graph along the y-axis and creating this mirror image. So again, it's going to have a very different domain because all of my x values are going to have to be negative, because when I substitute them into my radical, I will take the negative of a negative number, which will in turn become positive. So a reflection across the y-axis dramatically changes things like your domain. Now that we've had a quick recap of transformations on functions, we can take a look at an equation that has been transformed and see what kind of sketch we can build without using our calculator. So it says, without your grapher, make a sketch of the function y equals -3 times the square root of x plus 2 plus 4, and we're going to state the domain, the range, the intercepts, and where the graph is positive and where the graph is negative. So in this kind of situation, what we want to make sure of is that we understand the kinds of transformations that have been made. Sometimes I start from the very beginning of the equation and I just work my way from left to right. So this negative in front means the graph has been reflected, and you have to be very careful here that it's been reflected across the x-axis. So with that change in mind, and I'm not going to do a pretty or perfect sketch with this, but with that change in mind, instead of having, our original square root function, this function is now heading downwards. So that's the first change that I see. The next change that we see is with that with that 3 in front of your radical. So the 3 means there has been a vertical stretch by a factor of 3. So when I trace my graph now with a vertical stretch, we're actually going to be decreasing at a much quicker rate here. So this might be sort of an exaggerated picture of how our graph is changing or how it's decreasing as we trace it from left to right. The next change we want to make note of is that +2. That +2 is a horizontal change, and we know that horizontal change, so there's been a horizontal shift in this case. And that shift is happening 2 units to the left because we know it's backwards logically. So if I were to take the easiest point for me to manipulate, which is sitting at 0, 0 initially, and I move that 2 units to the left, that point is now here. So if I recreate this sketch, we've now shifted to the left a little bit, but the shape of the graph has been maintained. The last change we want to make note of is that +4, and that +4 means we have a vertical shift. And in this case, that vertical shift is happening by 4 units. Plus means up. So we're going to move this whole graph 4 units up higher from its original place. So if we move this graph 4 units up, the easiest point for us to manipulate becomes the point that's crossing our x-axis. So we are left 2 and we are 1, 2, 3, 4 units up. So that's going to be the new point where my graph sort of originates, and we can trace from left to right here. Now, if we're not really sure where this is going to cross the x or y axis, you might not want to make your sketch quite yet. What I can tell you is the domain and range of this function. So let's just make note of the domain and range. The domain are all of the x values from left to right. And I can see because of that shift 2 units to the left, we know the domain is now going to start at -2 for my x value and continue to positive infinity. Now, the range value, on the other hand, is low to high, and we know that this tail of the graph, the rightmost tail, sneaks down towards the floor. So the lowest end of my range is actually going to be -infinity, and my y value gets as high as +4 because we know we shifted this whole graph up by 4 units. So we have a range from -infinity to +4. Now we also wanted to talk about where the intercepts are. So over in the margin, we're going to remind you of how to find an x-intercept. When I want to find an x-intercept for any function, I know I have to let y equal 0 and solve that equation. So if we go back to the original equation, we have 0 equals -3 times the square root of x plus 2, all plus 4. So this is an equation we now need to solve. If I subtract 4 from both sides, I'll get negative 4 equals negative 3 times the square root of x plus 2. Now from here we want to peel away that coefficient in front of our radical. So I want to divide both sides by negative 3. So you've got 4/3 equals the square root of x plus 2. So we still want to try and solve for x. So in order to get x out of that radical, we're going to square both sides. So if I square the right side, I can square the left side as well. So 4/3 squared, 4 times 4 gives us 16 in the numerator. 3 times 3 in the denominator is going to be 9, and that's going to be equivalent to just x plus 2. So our last step here is to subtract 2 from both sides. So 16 over 9 minus 2 is going to be the exact location for my x-intercept. Now this is just a little bit of fraction work. We can say 16 over 9 minus, if we create a fraction out of 2 and make it 2 over 1, we can get a common denominator of 9. So 2 times 9 is going to give us 18 over 9, and we know that's equivalent to 2 over 1. So now 16 take away 18 is going to be negative 2/9. So when I make my sketch, I know this graph is going to cross that x-axis at roughly negative 2/9. So it's going to look something like this. So your x-intercept, and I can document this now, our x-intercept is at the location of negative 2/9, 0 for an xy ordered pair. The last piece of information we really want to calculate is the y-intercept, and we know for every y-intercept in the whole wide world, we don't want to let y equal 0, we want to let x equal 0. So we have negative 3, or y equals rather, negative 3 times the square root of 0 plus 2, all plus 4. So y will equal negative 3 times the square root of 2 plus 4. So in this situation, we already know that our y-intercept is going to be negative. This would just happen to be the exact value of that y-intercept. So we can say the y-intercept exists at the ordered pair 0 and negative 3 root 2 plus 4. So the last parts of analysis were asking us where the graph was positive and where the graph was negative. Again, the positive part of the graph is going to sit above until we hit that x-intercept. The negative part of the graph is going to go beyond the x-intercept and continue below that x-axis. So this graph is positive from negative 2, and I can say negative 2 is inclusive because if I put my pencil at negative 2, I am completely above the x-axis. So we are positive from an x value of negative 2 until we hit an x value of negative 2/9, because that's where your intercept is. We'll have a round bracket at negative 2/9 because that's a point that is in transition. So it's moving from being positive to negative. So the graph is now negative from that x-intercept of negative 2/9 forever afterwards. So we say from negative 2/9 to positive infinity. So that's the green segment of the graph that's sitting below our x-axis. Just be mindful that our knowledge of transformations and our knowledge of how to find both x and y intercepts were critical components allowing us to analyze this function completely. The last part of 9.6 involves finding the domain of a radical function algebraically. So when we ask you to find the domain of a function algebraically, it means don't use your calculator. You have to use your understanding of how functions behave and the rules for those functions in order to find the domain of these functions without your calculator. So what we want to mention first is that finding the domain depends on the index. So if we're dealing with a square root, it's a very different domain than something like a cubed root. We know that if an index happens to be odd, the domain is any real number. So we're saying for graphs like y equals the cubed root of x or the fifth root of x, the domain is automatically going to stretch from negative to positive infinity. It's the indices that are even that cause a little bit of a problem. If you have an even index, so if we're talking about something like y equals the square root of x or the fourth root of x, the domain must be found by making sure that the value of the radicand, so all that stuff underneath the root, is greater than or equal to 0. So what we would say with the square root of x is that in order to find the domain, we must make sure first that x, or all that stuff under the root, is greater than or equal to 0. So that tells us that our domain is going to be all values that start at 0 and increase to infinity. So we've just changed that inequality notation to interval notation. So let's practice with a few more examples here. So example number 2 says, find the domain of the following functions algebraically. So the thing you want to be very conscious of is whether or not you have an even or an odd index root. So if we're given y equals 3 times the square root of x plus 2, all minus 4, this is an even index root. So we have to be mindful that the radicand, or x plus 2, stays greater than or equal to 0, because we know we can't take the square root of a negative number. So this just becomes a little inequality for us to solve. So if x plus 2 is going to be greater than or equal to 0, then x must be greater than or equal to negative 2 if you subtract 2 from both sides. So what we would say, if you can imagine that negative 2 is that magic number and your x value needs to be anything greater than or equal to that number, this is the part of the number line that we're shading in. You can say that in interval notation, our domain starts at negative 2 inclusive, because we say greater than or equal to negative 2, and continues to positive infinity. So there's the domain for part A. The second function you're given, f of x, is equal to negative the cubed root of 2x plus 3. In this particular equation, we notice right away that it is an odd index, and we know regardless of what's happening in the radicand, when you have an odd index and a root, we know that the domain can be anything. So we're saying x can be from negative infinity to positive infinity, because we can take the square root, we can take rather the cubed root of a positive number, but we could also take the cubed root of a negative number. So in part C, we have f of x equals negative 5 times the fourth root of 4x plus 3, all minus 8. In this particular case, we see it's an even root, or it has an even index. So we need to make sure that 4x plus 3, that radicand, is greater than or equal to 0. So this just becomes a little inequality for us to solve. So if 4x plus 3 is greater than or equal to 0, then 4x must be greater than or equal to negative 3. At this stage, we want to make sure we divide both sides of your inequality by 4. So we get x being greater than or equal to negative 3/4. So if you can imagine on a number line, anything that's greater than or equal to negative 3/4 is included as part of your domain. It makes it easier to set this up in interval notation. So my interval notation is going to start at negative 3/4 and continue to positive infinity. Now in part D, we have a new function, y equals 0.4 times the square root of 5 minus 2x, all plus 4. Once again, because this is an even index root, we have 5 minus 2x must be greater than or equal to 0. So if negative 2x is greater than or equal to negative 5 when we subtract 5 from both sides, the next step has us dividing by negative 2, and this is where you need to take pause. So whenever you divide or multiply an inequality by a negative sign, you must flip the orientation of that inequality. So that's something that often gets forgotten in questions like this. So instead of being greater than or equal to, x will now be less than or equal to 5 halves. So when you think about values of x that are smaller or littler than 5 halves, we know our domain must start at negative infinity and continue to 5 over 2, again using a square bracket or being inclusive. In part E, we have an unusual radicand here. So we are given the function f of x equals the square root of x squared plus 4. Again, this is an even index root, and what we have to be sure of is that x squared plus 4 is greater than or equal to 0. Now, be very conscious of what's happening on the left side of this equation, or inequality rather. This is not just an x, this is an x squared. So if you can imagine choosing an x value and squaring it. So let's say we chose x equals negative 5. When you square negative 5, it becomes positive, and then you're adding 4 to that. So if we choose an x value that's negative, we are still going to be given a value overall that is greater than or equal to 0. If you choose x equals 0, hypothetically speaking, 0 squared is 0, but when you add 4 to that, you're maintaining that inequality, and we know that that's still greater than or equal to 0. If you choose an x value that's positive, of course, a positive number squared plus 4 is going to be greater than or equal to 0. So what we're trying to say in this case is it doesn't matter what type of x value you choose, when you square it and add 4, you're always going to have something that is greater than or equal to 0. So in this particular situation, the domain of this function can be anything. It starts at negative infinity and ends at positive infinity, because regardless of our choice, when we square this x value and add to it, we will ultimately have something that is greater than or equal to 0. Our last example is actually a challenge problem. This is one that's kind of tricky here. We've got f of x is equal to the square root of x squared minus 4. And once again, we have to say x squared minus 4 because this is an even index root must be greater than or equal to 0. Now, this is not the same as the previous example because instead of adding 4, we're subtracting 4. So there's potential for us to end up with a negative in that radicand. So we need to be careful to avoid those values of x that are going to give us negative values overall in that radicand. So if we were to continue trying to solve this inequality, let's say we add 4 to both sides. So x squared is greater than or equal to positive 4. Now we know with equation work, in order to get rid of a square, we need to square root both sides. So essentially what happens is when you square root something yourself, you have to include plus minus. So plus or minus the square root of x squared is going to be greater than or equal to plus or minus the square root of 4. And boy, this starts to look confusing. So we say x must be greater than or equal to plus or minus actually on both sides, plus or minus the square root of 4, which we know to be 2. I find these quite confusing sometimes, so I'm going to show you a technique where you can choose some test values to see where you're actually going to get x's that are positive or negative. So I'm going to move over and I'm going to plot two values of x because we're getting a plus or positive 2 and a negative 2 as values that we need to be mindful of. So if I plot negative 2 and positive 2 on a number line, what I'm going to do is to choose test values in each of these intervals for x. So we're going to pretend that this is our x number line. We're going to choose a value of x that is somewhere between negative infinity and negative 2, and we're going to see if overall we get something positive. So if we were to test, let's say x equals negative 3. So this is our first test interval. We can label it that way. If we test x equals negative 3 in our inequality, we get negative 3 all squared minus 4. We need to see if that's actually greater than or equal to 0. Well, negative 3 squared is 9, and 9 minus 4 is positive 5. So if we're choosing something that is less than negative 2, we're ending up with a positive radicand. So that will work in our favor, and that'll be part of our domain. Now let's pick something in this middle interval, somewhere between -2 and +2. So in that second interval, I might test something like x equals 0. So if we do that, 0 squared, I'm just testing the radical here, 0 squared minus 4 is going to give us a -4, or 0 minus 4 again is negative. I know I can't take the square root of a negative number, so this middle interval is out. It's giving me a radicand that's negative, and we know we can't use those values of x because we can't take the square root of a negative number. So the third interval we want to test might be something like x equals +3. So if I test x equals +3, once again we have 3 squared minus 4. 9 minus 4 is actually +5, and we can take the square root of 5. It's just an irrational number. So we know this is going to give us a positive part in our radicand. What that means is we will have domain, or x values on our function, that are less than -2, or less than or equal to -2, or we can choose x values that are greater than or equal to +2. So we're going to have two distinct intervals here for domain. Our domain is going to start at -infinity and continue to -2 inclusive. And then we're going to put a little union because there's a second interval in domain. And that second interval is going to start at +2 and continue to infinity. So as long as we're choosing x values within those intervals, we know we're going to get valid parts of your graph. Again, this last example was a challenge question. It's just kind of interesting to see how these challenge questions can be sorted. Now you're ready for your 9.6 regular homework questions. Please have a look at numbers 1, 2, 3, only A through D for number 3 here, and question number 4. As always, if you have any questions whatsoever, please don't be shy and reach out. We're happy to help you at any time.